this is problem 8 of Neetcode 150's valid Sudoku. So we're going to be given a board which is going to represent a table of Sudoku, and we're going to have to determine whether it is valid or not. So you probably already know the rule of Sudoku. For each rows and for each columns, you can only have a number once. So if, for example, I had the number 1 in the first row, well, it's going to be an invalid Sudoku. And also for each square of 3 by 3, I can only have each numbers from 1 to 9 only once. So how are we going to solve this? First, we're going to have to index our rows and index our columns and create a dictionary for the rows and also a dictionary for the columns. So you can see here that in my dictionary, my rows indexes are the keys and the columns are the values that are within this row. So for the row with the index 0, I have the values 1, 2, and 3. They are here. For the row with the index 7, I have the value 4, 1, 9, 8. Same concepts for the column. So for a column value with the index 8, I have 3, 4, 5, 6, 8, and 9. And this way we can easily check if the value that we're looking at is already within the row it is in or the column it is in. And lastly, we have to also create a dictionary for the 3 by 3 squares. So we're going to have to use the x and y values to specify which 3 by 3 squares you want to look at. So here, our square at 0, 0 represents this one. Our square at 0, 1, it's this one. 0, 2, it's this one. 1, 0, it's this one. And you understood the concept. And you can see that for the square 0, 0, we add the values 1, 2, 4, 9, 8. 1, 2, 4, 8, 9. And it works. So let's code this now. So first, let's create our dictionary for our columns, for our rows, for our squares. And in this case, I will use a default dict. So let's go ahead and code this. All right, we have created our 3 dictionaries. And now we want to loop through each rows. And for each rows, you want to loop through each columns. So we're going to say for R in the range 9, for C in range 9. And first, you want to check if we have a dot, because a dot represents an empty case. So if the board at this row and at this columns is a square, just want to continue. All right. Otherwise, you want to check if the board is in the row, or the board is, well, the value of the board at this row and this column is in the column or in the square. So this is where we're going to do all our checks. So we're going to say if the board at this row, at this column, in rows at this row, or board at this row, column is in calls at this call, All right, and for the squares, we're going to use an integer divisions to get the index x and y. All right, so we're going to say row integer division 3, meaning that for the index 0, 1, and 2, we're going to get something like 0 point some values after the comma. And basically the integer division is only going to take the integer without the rounding. So we're going to retrieve our 0 this way. Same thing for 3, 4, and 5. If we divide 5 by 3, we're going to get 1 point something, and we're only going to retrieve the 1. So this is how we're going to get our indexes for the squares. All right. So that's how we check it. And if one of these conditions appears to be true, well, it means that we don't have a valid Sudoku. All right. And after this, we're just going to append the value at this particular row and add this particular columns, to the row, and to the square. So let's do this. And here we have to use our integer division again. All right. And if after looping through all the rows and all the columns for each rows, we never return false, it must mean that we have a valid Sudoku. Okay, so this is the solution for the problem 8 of Neetcode 150. Oh, we have an error. Rows. So rows is not defined. Oh, okay. Oh, calls twice. All right, so this solution is looping through every rows, and for every rows it is looping through every column. So it has a time complexity of n squared, and also we're adding multiple items for each rows in our dictionaries, meaning that we also get a space complexity of n squared. There is a better way to solve this problem, not a better time complexity, but a better space complexity. So we can solve this in O of n. And instead of using a dictionary, we're simply going to use an array as follows. And this way of solving this problem is called the bit mask. So we're going to use the bit digits. It's a little bit harder to conceptualize, but you will see that it is pretty convenient once you understand the logic. So we're still going to loop through every rows, and for every rows we're going to loop through every columns, and we're going to check if the board at this particular row and at this particular column is a dot. If it is, we're going to just continue. But what we're going to do is that we're going to want to take that value and convert it to a bit within 1 and 8. So since our values are ranging from 1 to 9, we're just going to create a value that will turn um, the value at the row and at the column of the board into an integer, and we're going to remove 1 to it. So right now, if our Sudoku has a 1, well, it's going to return a 0, and if it has a 9, it's going to return an 8. All right, and after this, we're going to do this this technique. You might not be super familiar with this, but it basically tells that turn on the bits at this value. So if I turn the bits 1 on at the index 0, you can see here that at the end, if I'm taking a bits ranging from index 0 to 8, well, the index 0 right now is turned on. And here on the left side, you can see that I'm turning on the bit at the index 1. You can see the result here. Just under it, you can see that I'm turning the bit on at the index 2. And what is convenient is that we're basically gonna get a bit of length 9, and we can add them. So for example, if I have turned a bit here at index 3, the value itself is 8 because, as you can see here, it basically doubles every time. So at index 0, I have 1. At index 1, I have 2. At index 2, I have 4. At index 3, I have 8. All right. So you can see that at index 3, when I turn on the bit, I have a value of 8. Same thing here. When I turn on the bit at index 4, I have 16. And you can use this symbol here to say add this bit to this one and do not remove the first one. So you can see that the result of this is 24. Okay, it is a little bit more complex, and you probably won't need this technique to solve the question in your interview, but it still helps you to reduce your space complexity from O of n squared to big O of n. All right, so what we're gonna do is that we're gonna check if basically, all right, so if this value, the n sign just mean if it is inside or if it contains calls C, we're going to return false. Okay, and you're going to see why later we use call C, but basically we're going to add this bit mask value to the row. All right, so we are going to do the same thing for the rows now. And for the squares, it's going to be a little bit different from what we saw previously, because in this case, we don't have a dictionary. We have an array with 9 inputs. All right. So for each input, we're basically gonna add each bits to that input, and this way we can find whether the bits we're currently looking at is already in that index in this array. So we're still going to use our integer division. But instead of having x and y values, we're simply going to add both. So we're going to do, again, this divided by 3. But we're going to have to multiply it by 3. And I'll show you why. Right? Because now we want to, we have 9 entries in our array. So we want to be able to eventually access the index number 8, which is the last one. So by doing this, we know that our row divided by 3 as an integer division cannot go higher than 2. So the higher that both are going to get, it's 2 times 3 plus 2, which is 8. So this is how we get our last index. Right? Return false. And after this is where we're going to add rows R with this symbol, which means add this bit to the current bits. So we're going to do the same thing for the calls. All right, and for the squares, we're going to add this here. Again. All right, and if after looping through all of these, we never return false, well, it must mean that we have a valid combinations. So this is the bit mask solution. It is a little bit more complex. All right. So you see that it works. The problem itself suggests to use space complexity of n square. So it is not required for you to show up to your interview and bring the bit mask technique. But if you can, I think this is gonna be quite impressive, as it shows skills that few people masters. So these are the two techniques to solve the valid Sudoku problem. The first one is the hash it, which is probably the cleanest one and the easiest one to understand. And the second one is the one we just saw, the bit mask, by using bits, basically, like this, and solving for the valid Sudoku. So thank you for listening, and I hope to see you in the next video.